All right. A lot of people dropping in. Hi everyone. Yeah, let's get started. So it's first 12. Yeah, but before that, because of the upcoming alarm testing, please we indulge everyone to kindly silence your phones, or if you can also get it off so that it's not disturb the speaker during presentation and other audience as well. Yeah. So so welcome to today's biomes. And over 15 years now, YSE has held this seminar series, and it's being named BIOMES, which is the school flagship forum for bringing cutting-edge research and impactful work to the YSE community. BIOMES stands for Bridging Issues and Optimizing Methods in Environmental Studies. And this week, we are glad to be joined by our very own Dr. Malone. Dr. Malone is Assistant Professor of Natural Carbon Capture at the Yale School of Environment with the Center for Natural Carbon Capture. She studied the carbon fluxes. Dr. Malone obtained her PhD in the University of Alabama, where she studied carbon fluxes in subtropical wetland ecosystems. She then worked for the USDA Forest Service at Rocky Mountain Research Station from 2014 to 2017. And at Florida International University from 2017 to 2022. At FIU, she established the Malone Disturbance Ecology Lab. Her primary research focuses on improving our understanding on how climate and disturbances regime influences spatial and temporal variability in ecosystem structure and functioning. She explores questions related to ecosystem conditions, sustainability, and vulnerability to climate extremes using remote sensing and eddy covariances. In the fall 2022, she joined the Yale School of Environment and the Center for Natural Carbon Capture, YCNCC. Dr. Malone also received numerous awards and honors, including Ecological Society of America Early Career Fellow, Florida Coastal Everglades Long-Term Ecological Research Collaborator of the Year, NSF Early Career Awards, and among others. With that said, I would like us to welcome Dr. Malone to do her presentation. Thank you so much.
So, oh, I already forgot. You can hear me now? Perfect. Ecosystems have a pretty big effect on the global climate system through energy balance, regulating water vapor, and cycling greenhouse gases. But these changes that are occurring in our dynamic system are creating feedback loops that make it really important that we actually understand to a really, really high resolution how ecosystems are feeding back to the climate system, how that's changing over time, and what does that mean for the future. And so in today's talk, I'm going to focus on two major topics. One, looking at the effects of sea level rise and freshwater management and how that's reshaping our coastlines. And the second, on reducing uncertainty in the methane soil sink. So I have you for about an hour trapped in this room, and you're going to hear about the latest things that I'm really excited to learn about, because I do think it's going to be really important for training environmental scientists to recognize that their actions on landscapes have really important consequences for the future. And so first focusing on sea level rise. And when it comes to sea level rise, there are a couple big issues that we do have to be concerned about because the ocean is coming. But one of those other issues is that we need to make sure that terrestrial systems remain resilient. And by resilient, I mean we need them to keep capturing carbon because that will determine what terrestrial systems will be able to stay terrestrial and not become aquatic. And along coastlines, we want them to stay terrestrial. And so for this study, we're going to focus on understanding where low productivity zones are developing along coastlines and what does it mean for carbon capture. We care about this because wetlands are super important. They represent only 5 to 8% of land cover, but they contain 32% of soil carbon. And that's because wetlands are storage ecosystems. Because of their inundated conditions, carbon that's produced via vegetation accumulates in these ecosystems, not above ground, but it falls into water where it breaks down at much lower rates. And so this is why when you think about wetland systems, at least the first thing that haunts me is, am I going to sink into the soil as I'm walking out to my research site? Because I've been stuck plenty of times. You're going to see a picture. But all of that soil is containing so much carbon. And so there's so much value, not because these systems capture a lot of carbon at really fast rates, but because they store that carbon in the soil for a long time. But all of that carbon that's stored in the soil, if it's exposed, it can go back to the atmosphere in a fraction of the time that it took to accumulate that carbon. Well, globally, unfortunately, we have been developing wetland ecosystems. And most of the time when we develop wetland ecosystems, it's for agriculture. Because when I said that wetland ecosystems are really good at storing all that carbon below ground, which is really good for growing crops. And so we have been developing wetland ecosystems and converting them for agriculture for centuries. And because of it, we've lost about half of the wetlands that existed in the past. And we've lost that due to a combination, mostly agriculture, but also for urbanization because wetlands occur on the coastline. And as a true born and raised Floridian, it's beautiful. You want that house on the coast with the beach, you know? And so because of it, there has been a lot of conversion of wetland ecosystems for urbanization because we love to live in beautiful places. There's a new problem with sea level rise. Sea level rise isn't itself a new problem. It's been happening for a really long time at really slow rates. But now it's happening at really fast rates, rates that are really concerning for coastal systems because we know that this could be a challenge. And so we're used to rates that are less than 2 millimeters a year, and even that would have been considered fast a couple decades ago. But now we're looking at rates that were recently clocked at almost 6 millimeters a year increase in sea level rise. And for a lot of areas, they're not that concerned because they're not at sea level. But for areas that are at a low elevation, this is a pretty big problem. In the past, wetland ecosystems are able to respond to sea level rise by being productive. You grow vegetation, some of that vegetation falls to the soil, becomes part of the soil, you keep accreting over time, and you can keep pace with sea level rise. But that was when rates were a little bit more reasonable. Now that we have exaggerated rates, we are really concerned about whether ecosystems can keep pace, even though there are a number of feedback processes that suggest they can do it, but under very certain conditions that are dependent on what we're doing in the rest of the landscape. But there's one area, lucky for us, the Florida Everglades, which is the front line for global change. And what this means is that things are happening in this region before it's happening in the rest of the world. And part of that is because One, we've messed with this landscape in ways that I'm really impressed with, like that we can pull off projects at the scale that we've had so that people can live in these areas. Impressive. But also because this area, before we fully recognized it, we need these natural processes to continue for people to continue to live there. And so here you're seeing some estimates of sea level rise, not in the far off future, but this is like coming up now. These are areas that are already experiencing the signs of sea level rise. Part of that we know because South Beach is running pumps to keep the ocean out of the streets, and that's happening 24/7, whether there's a storm or not. And in parts of the landscape for events like king tides, the ocean comes in and welcomes us all and makes us all really realize that most of us are living in oceanfront properties if we let the system really go. But this is a real concern for natural processes that we're relying on in this landscape. And we've known that for a while, which is why the largest global restoration project is the Comprehensive Everglades Restoration Plan, where historically water would flow from Lake Okeechobee in the middle of the state and it would flow south. And so all of that area was inundated during certain parts of the year. And this process was really important for keeping ecosystems healthy, keeping them productive, and keeping them in a system that could keep pace with sea level rise. But we like to eat in Florida, and we need to make sure that there's sufficient agricultural production in this state because the weather is really good and you can grow anything there. And so a lot of the land in between Lake Okeechobee and South Florida was converted into agricultural area, the number one terminator of wetland systems. And with that conversion came a lot of big problems. Fires became really uncontrollable because we exposed all of this land. We started to notice, oh, you can't just drain wetlands. It becomes a huge problem because you lose your soil. And when you lose your soil, you lose your elevation. And when you lose your elevation, you start sinking further into the earth. And so that became really apparent. And Florida panicked a little and said, you know what, maybe we can't just do whatever we want. We can't move the water wherever we want. Maybe we should try to mimic some natural patterns. We came up with a comprehensive Everglades restoration plan and started to improve the water flow from Lake Okeechobee, get it down south. It was really important to get it south into Everglades National Park because we really wanted those ecosystems to remain natural. And so we created a project, increased the flow of water, and over time, different elements of the project are being executed. And we have a lot of questions about, is it effective? Are ecosystems doing well? Let's see. Okay. So what we're concerned about looking at for understanding how well ecosystems are doing, we need to track patterns in peak collapse, which is essentially where you're losing your soil surface, vegetation is dying back, and you can't hold on to your soil without the vegetation, even though Florida is flat. We're also looking for patterns, characteristic fires. We're looking at where the peat is exposed. And most importantly, we're looking at coastlines to follow signs of saltwater intrusion. Because if you don't have enough water flowing into these natural systems, you don't have enough fresh water pushing up against the salt water to kind of push back the ocean. And so for this talk, we're going to focus on saltwater intrusion and how that's changing ecosystems. But I just want to be clear that all of these processes are just pumping carbon back into the atmosphere. And with all the carbon that we're pumping into the atmosphere with our own shenanigans, we don't need the natural systems pumping carbon into the atmosphere. And so we're actively trying to manage these lands to hold on to that carbon. And it's not only important for our global carbon budget, which I value strongly, it's also important for just keeping the soil in place, because if we don't have the soil, we can't continue to live along these coastlines. And so for this study, we're going to focus on some work that was done by my master's student, Amanda Ricci. And she was really focused on trying to understand, well, what's the difference between carbon capture in this landscape? And so an important feature of this landscape is the difference between ecosystems. And so one prominent ecosystem that we're relying to hold our coastlines together, mangroves. And so even though in part of this landscape they exist as tall forests, in the part of the landscape that we're focusing on, they exist as scrub mangroves, still cute and very capable of taking up a lot of carbon and putting it in the soil under all that good water. These mangrove ecosystems, they're generally temperature limited. And so what really keeps the mangroves along the coastlines isn't just their dependence on salinity and what comes in with that ocean water, it's also temperatures. That's what's keeping your mangroves at your coast. And whenever temperatures start to rise, like they are now, you'll get mangrove encroachment, mangrove ecosystems that are coming further and further inland. And whether that's a good or bad thing depends on your values. But in this system, it wouldn't necessarily be bad for a number of reasons. And so we're just trying to track, is it happening and what are the costs of it? If this were to happen very successfully, you should have the mangrove scrub moving in to freshwater systems. And for the part of the landscape we're focusing on, it's going to be freshwater marl prairies, and it should look like this picture. That's not bad. If I looked at that, I would not be very concerned. I'd be like, okay, there's some change happening, but conditions are changing, the landscape is responding, and that's looking pretty good. The problem is, though, it doesn't always happen with grace and dignity. And it becomes a problem when your salt water is moving faster and at higher concentrations than the vegetation can deal with. And when that happens, you will have mangroves coming in slow and steady, but you will lose your graminoid species, which means everything in between the mangroves is loosey-goosey, and that's how I got stuck out there and had to be pulled out of the mud. And so with the loss of your graminoid species, you don't have such a beautiful transition, and all areas that are experiencing this in between are in trouble given the right event, because all of that soil is loosey-goosey in there. And some waves coming through there, a nice good hurricane, which is happening every few years, could lead you to lose a lot of that soil. And so we are concerned. How much of the landscape is experiencing that? And what does it mean right now for carbon? And so Amanda designed this study, which focuses on utilizing information from eddy covariance towers. And so while we won't go into the detail of eddy covariance, I will tell you, this is how we can measure fluxes of carbon in and out of ecosystems. And so we want to take this information from the different ecosystem types, and then we can use it to estimate what's the capacity for these systems to capture and sequester carbon. We also want to take some information from South Florida Water Management District, who has been measuring and monitoring water levels and salinities throughout these different ecosystem types. And we want to see, well, what is happening with these two patterns together. We have some expectations for water levels should be increasing because, sea level rise, but also because of SERP. The restoration will increase water flows into this system, but we also know that salinity is going to be increasing because, sea level rise. But the degree to which salinity is going to increase is going to be dependent on how much fresh water can continue to flow into these ecosystems. In addition to looking at the patterns in hydrology, we also have to consider, well, what does water level really mean for these ecosystems? And for that, we calculated this idea of submergence. At different water levels, different parts of the canopy is going to be submerged. And the expectations is that if you submerge parts of the canopy that are photosynthesizing, we know that that's going to be directly related to our carbon exchange rates. And so we divided these ecosystems, some of their time based off of what the water levels were and what does that mean for canopy, and we call this submergence. We also recognize that the conditions for submergence is going to be different between the different ecosystems, and so we try to account for that. We take all this information together with the fluxes, and we try to estimate, well, what's the maximum rate of carbon capture? And we start to note these maximum rates of carbon capture, not just between the different ecosystems, but how they're responding as conditions are changing. Because we think, we went out on a limb here, but we think that if a system is spending less time at its maximum, that might be a sign that that system is in disequilibrium. Essentially, if the system is actually evolved to handle the conditions that they're currently experiencing, they should spend more time at their maximum photosynthetic rates, or you run the risk of being converted to something else. And so we came up with this idea of how to estimate the climate debt of different ecosystems by measuring when optimum conditions are happening in that system, when it's taking up the most amount of carbon, and then how does that change as conditions change. So you get that difference. But then you multiply that difference by the duration, the amount of time the ecosystem spends at that. And when you sum it all up, you should be able to figure out which system is experiencing conditions that are not conducive to carbon capture. And then we consider this a climate debt. And even though you would think, well, it's sea level rise is included in climate debt, as are any changes in disturbance dynamics. And so what we're really focusing on is how well is carbon being captured in freshwater ecosystems compared to the mangrove scrub, and in the middle, in the ecotone, where you have conditions fluctuating pretty extremely. And you can see how raggedy this vegetation looks in that understory. Like, it's barely holding on, still holding the soil in place. But once that vegetation really dies back, if the mangroves can't expand into it fast enough, it's going to be a situation. And so we're measuring carbon dynamics under these conditions. And so the first thing I'm going to show you is how the difference in maximum photosynthetic rates, which were calculated by the eddy covariance towers, how that varies with water level, and what did it tell us about the system. And so if you look at the blue line, which is for freshwater ecosystems, you see that their maximum rates are actually occurring when water level is at or below the soil surface. But as water levels increase, we have a decline in maximum photosynthetic rates that can be 20 to almost 35% decline from the optimum. For mangrove ecosystems, we can see that their change in maximum photosynthetic rates isn't much, but they're still higher when water levels are above the soil surface, which makes sense because if salinity gets too high, you can have hypersaline conditions, and that's going to lead to a decline in productivity. For the brackish ecotone that's kind of existing between the two ecosystems, we see an in-between response, where these systems do really well when they're on the drier end of things, but as water levels begin to increase, we can see a slight decline. When we multiply that by the duration, what we see is that the climate debt is highest for marl prairies, second for ecotone, and then the mangrove scrub are out here living their best life, which really explains why we're seeing them move into other ecosystems. And so this calculation of climate debt may be a good way of making estimates for which ecosystem will become something else and what that something else might be based on the debt that's developed. When we try to express exactly what the carbon cost is of this debt, we can take our observed net ecosystem exchange rates and compare them to what they would be if the system was able to operate at its optimum for the majority of a year. And as you can see, the climate debt is much greater for the freshwater marl prairie than it is for the ecotone, and it's still there for the mangrove scrub as well. But altogether, we see that the patterns in net ecosystem exchange rates, they do explain landward movement of coastal wetlands. Carbon is captured to the highest level in mangrove scrub and declines as you move further inland. Low resilience to current conditions is evident in marl prairies, and we know that this is a legacy of draining, where marl prairies became dominated by sawgrass, which does better under drier conditions. But as SERP continues, we expect these ecosystems to show improvements because species that currently exist within them should become more dominant over time as water levels are restored. In the southeastern saline Everglades, we estimated about 115 metric tons of carbon being captured in 2021. And if the ecotone continues to advance at a rate of about 25 meters per year, we would project that there should be a 12% increase in carbon capture in the future, because even with those degraded areas eventually become mangrove scrub. It usually takes a decade or so for that to happen. And then we expect an increase over time if it's possible for that to happen. But in order to understand the likelihood of that happening, my postdoc, Boya Zhang, has been working on figuring out where and when are these patterns changing on the landscape, using remote sensing techniques to understand what's our potential for loss. What's the ability of this system to actually convert from one class to another? And so for this work, he's focusing in the same region, the southeastern saline Everglades. He's interested in understanding where degraded areas are occurring, where they're transitioning or in between states between degradation and a fully vegetated zone, which is a high density of vegetation. To remind you of what this might look like, we have those mangrove scrub looking beautiful, luscious, and green. And then if we have that successful conversion, they would move over into these in-between areas. Those two at the top are considered vegetated areas because we have that successful conversion without the exposure of soil, which means the vegetation densities are sufficient to keep everything where it is and to capture carbon everywhere we need to be capturing carbon. What we're concerned about, where you see me, you see that? You see I have feet, but you can't see them because they're sinking down into the mud. In these systems where the vegetation starts to die back, they're just not doing as well. And so we want to know what's the conversion between these different ecosystem types. How much of the landscape is staying in these states? And so Paul was able to develop a strategy to detect these ecosystems, create these classification maps and these annual maps. We did it creatively by using information from Google Earth, where they have high resolution information allowing you to classify locations as either degraded, transition, or vegetation zone based on how much of the soil you can see. And we can create these annual maps, measure change over time for those annual maps to get rates of change between the different classes, and compare those change rates to patterns in salinity. Based on the rates of change, we can then make projections into the future because we're feeling bold. So we're able to show we can do this. We can make these models, and they're pretty good at being able to distinguish between vegetation zones, transition zones, and degraded zones. And so that gave us the confidence to say, let's move forward. Let's make those classification maps and let's see what's changing. And when we look over time, we can see most of the landscape is in that transition area. And so this area is largely affected by sea level rise. We do see stable areas that are in that vegetation zone, so that's promising because over time we want those vegetated areas to expand out. And what we see when we're looking at degradation, not so promising. So in the 80s, our degradation rates were a little bit better than they are now. They've been steadily increasing over time, which is a response to climate as well as to disturbance dynamics and to freshwater management. If we wanted to know which classes are changing into what other classes, we know a lot of the change is happening between that transition zone, which could fluctuate from being degraded or becoming vegetated. And that's happening a lot over time. And we know that this is almost an expected pattern because the patterns in precipitation over time in the Florida region is highly dynamic. It responds to things like El Nino Southern Oscillation, which will lead to either longer or shorter dry seasons. And so this amount of change we do expect over time, but we are interested in the trends. And so we start off with most of the landscape being in this transition zone. And by the time we get to 2023, that's still a dominant class, but we have much more of the landscape that's in this degraded area and much more of the landscape that's kind of supporting more vegetation. And so that is promising. But one thing that we do pay attention to is the fact that these patterns are not consistent everywhere. It's not even. There are certain parts of the landscape, like the western half of the southeastern saline Everglades, that show stronger vegetation growth. And in the central part of the southeastern saline Everglades, we see a lot of transition area being supported. And then in the eastern part, that degradation is alive. And we see the growth of degradation in that region pretty strongly. These regions correspond to what we know about the hydrology. And so there are parts of the landscape that are still experiencing very strong trends in salinity, where salinity is, of course, increasing everywhere, but these areas are seeing stronger increases. And part of that stronger increase, we believe, is also due to freshwater flows. If you can't flow that fresh water in there, then you have nothing to really fight against those hypersaline conditions developing. Versus the western part, which gets access to more freshwater flows, and because of it, the vegetated areas are doing well with continuing to grow and expand. When we look at what the future might hold for these areas, we take the rates of change that are present in the different regions that are experiencing different things. And so some regions have more freshwater flows. If we took their rates of expansion into an optimistic scenario, we would believe that vegetation zones would increase into the future if you could increase freshwater flows, and we should see a marked decline in a transition zone and a stabilization of degraded areas. But if we're not able to maintain the freshwater flows into these areas because we abandon SERP or conditions go haywire, then we are going to see some problems. We're going to see current enhancement of the degraded areas, which will overtake both transition zones and vegetation zones and will become significant issues into the future. And if we continue on with our business as usual, we expect the patterns that we see to kind of continue. But what that could mean is surprisingly an increase in the vegetation zone, but that vegetation, the degraded area, is following close behind it. And so it would be really sketchy. And so if we had to make a recommendation, definitely we need to continue on with this freshwater management because it has really important implications for our ability to maintain the coastlines. And we know this because of the relationships between these extreme salinity conditions and the development of these degraded areas, which will become hotspots of loss if we don't facilitate successful transitions from coastal ecosystems into coastal ecosystems further inland where they'll need to go in order to respond to the changes in conditions. Now, if you want to know exactly how and why this works, you can see Cindy's talk where she's focusing on how exactly are we detecting low productivity zones. And she's giving a talk in Confluence on December 4th. And she's a Master's of Forest Science student. Cindy, I hope you're here. Shout out to you. We look forward to seeing your great research. So this project, we're started off focusing on carbon dynamics in these three different systems, looked at how those different systems are changing on the landscape. Your question, where are we going with this? Of course, we're going to build a carbon model that responds to all these changes and allows us to estimate what's the actual carbon cost of these changes into the future. And so this research was funded by my NSF Career Award, where we are really interested in securing our coastal ecosystems. And this work will eventually feed into process-based models because that's what we're doing all this for. We want to develop these huge models that incorporate all the important effects globally. And right now, we are at the point where we can put in the physical laws into our process-based models, but eventually we're going to get to the world where we can include the effects of sea level rise, where we're including the effects of droughts, hurricanes, fire, pests, and pathogens, at a large scale. And so a lot of the work that we're doing, we're also looking for the parameters that we can put into these models so that we can know what's the impact globally. And a good example of that is in our project where we're focused on reducing uncertainty in the methane soil sink. So if you came in this room, you know there's going to be some methane. Just a little bit, not too much, okay? And so atmospheric methane, it's been real steady for a really long time. And so eventually, of course, we're going to get to the Industrial Revolution. It's going to take off. It's going to accumulate in the atmosphere, and we're going to have a lot of questions about it because we do know most of the accumulation in the atmosphere that we're seeing is, of course, because of us. We did it. We're guilty. But some of this accumulation is also due to feedbacks from natural systems. When we look at the global methane budget, you can see that for all of the natural emissions, we give two numbers. We give a top-down number and a bottom-up number. I'm a bottom-up person, but I love the top-down people. We work together. But they're going to give you two different numbers. And that's because there are different ways of measuring these different effects, and the way you bring them into models has a really big impact on the number you get, but also because we're not putting in a bunch of processes that we know are important because we haven't figured out how to do that yet at a global scale, but we're working on it. And so the way we understand what's happening is that we need to take information from the atmospheric community and we need to pair it very well with what's happening at the surface. And the bottom-up people, we control the surface and how it's measured. But there hasn't been a lot of opportunity for us all to come together and figure out how should we bring this all together in a way that will lead us to have the same numbers and to believe the same things, because we're looking at each other with a lot of side eye. And so we propose to bring together a group of people who are open and willing to kind of work on these problems slowly and steady over time. And so myself, Yumi Oh, Gavin McNichol, Li-Ching Liu, we all propose this idea to bring together atmospheric people with bottom-up people who make measurements in all different ways into a group. And we started off with a very basic project that we submitted to the DOE, and they supported us. We appreciate them. Then we submitted our group to grow it because we have some problems that our expertise wasn't sufficient for, so we needed more people. And so then we submitted a proposal to YSE, which they supported us, and we love them for it. And then last week, we got Spark Climate Solutions to support us so that we can continue to work together on problems in the future. But for this talk, we're going to focus on one very specific problem that we were able to eat away at over the last year. And so one of the major activities of our working group was that we went out there and we got all of the chamber data that we know exists. We got this information from papers. We got it through data sets that existed on someone's computer. We got it all. We took all of this data. We put it into one big data set. We took that information, compared it, and added onto it with all of the flux data that we know exists. We took all of the atmospheric inversion model simulations and the process-based models, and we put them all into this information system that now we can use to answer all kinds of wild questions that we come up with. We have a number of people that are leading different groups. We have ones that are focusing on perspectives and AI and ethics because it's the Wild West out here. We can do whatever we want, but maybe we should come up with good strategies of doing it well. And so we have a group focused on that. We have a group that's right now focused on the global methane budget and variability. We have a group focused on incorporating more microbial processes into models. And then, of course, hello, I'm in here. We have a disturbance group. And we're focusing on what are disturbances doing to methane dynamics and what does that mean for the future, how to get this stuff into these models. And the first problem that we decided to approach was a little low-hanging fruit. We're focusing on methanotrophy. And so when methanotrophs are exposed to atmospheric concentrations of methane, they can oxidize that methane, but at really low rates. This approach is really simplified in process-based models to the point where we think it's just kind of consistent and we scale it by area. What we focus on in process-based models is understanding what's happening with wetland areas where a lot of methane is being produced. And so a lot of methane is also being oxidized in these areas. And we're largely ignoring high affinity methane oxidation, which recent studies have shown is very variable with temperature dynamics. And because of it, it means that how we're representing this in models is not appropriate. And we could potentially be underestimating the soil sink for methane to a large degree. And when we wrote this proposal to DOE, we were like, oh, it could be twice as high. We were very hopeful. But we're going to find out just how high it is. Okay, so we took all the information that we gathered for the infrastructure that we built. We paired this with 2 different process-based models. We used the chamber-based data to come up with not only the parameters to include in the process-based models to incorporate the high affinity methane, but we also created a machine learning model to see how well can we use that information on its own. And then we paired it all with atmospheric inversions, which we're using as our standard. If you can match what the atmosphere says, then we think we're doing a good job. Just to remind you, we're focusing on a really small part of the budget, which is the soil sink, which is currently estimated at about 30 teragrams of carbon per year. So if you look on the bottom, these are the original process-based models without our inclusion of HAM, our high affinity methane, and LAM, our low affinity methane. And so that's the wetland effect plus the high affinity methane, what's happening in terrestrial systems that have lower concentrations of methane. When we built those processes into the process-based models, we estimate if you include both HAM and LAM, you'll end up with a 30% increase in the methane soil sink, which, okay, it wasn't as much as like half like we boasted about in our proposal, but it's a lot. That's a pretty big difference. And if we don't separate out HAM and LAM in the models, we're actually going to overestimate. So don't do that. We've already figured out that would be a mistake. Not a good place to go. But when we compare what would happen if we put this in our process-based model, which is our HAM, which is the most colorful map, to what happens if we try to just upscale this with machine learning, do we have enough data? You can see the colors don't match. Some of the colors that are over in the HAM-LAM are not over in the machine learning model. So that's a problem. That means that we're not capturing the spatial variability. It's also an issue that if you looked at our process-based model, if you looked at the trend that we would project over time, it's much more steep, much more dynamic with increases in temperature and increases in atmospheric methane concentrations than our machine learning upscaling, which means we don't have enough data to try to do this with machine learning on its own. It's not sufficient. We're not there yet. I keep trying, but we're not ready. We also compared this to atmospheric patterns with carbon tracker methane. And what you really want to see is you can't see anything behind the green line because then that means everything is falling in line. Everything is giving you the same estimate. And when we see trends in the atmosphere over time globally, it's not doing a bad job. Our HAM-LAM model and even the machine learning model isn't doing a terrible job at that, even though it's not as good, but it's close. But when we look at the isotopic signature of methane in the atmosphere, you start to see, okay, we got some problems. All these lines are not behind each other. I can see all those colors. It is a problem that we're not really capturing that pattern the same way. You can see we get the general dynamics, but there's still a lot more processes we need to build into these models before we're going to get the isotopic signature correct. But we did figure out that the soil sink is looking to be a bit higher. We're estimating that it's about 42 teragrams of carbon per year, which is a good sign. We did clearly see that our process-based models, they capture the atmospheric variability more realistically than our machine learning models because we don't have enough data to do that yet. And we still need to include more processes to get the atmospheric isotopic signature to match what we see in the atmosphere. So lucky for me, we still have work to do. And so we're focused on including more information on variability, more on microbial processes, and of course, my group, disturbance group, more information about the disturbances to try to get those patterns to line up well. And so none of this would be possible without the amazing people who work in my lab. Scientists that are working at all levels, studying plants all the way up to ecosystem level studies and global studies with upscaling, all with very different skills. Some focus on atmospheric dynamics, others focus on how the reflectance of individual plant leaves change with nutrient conditions. And so all these people are working to add their contributions to the large scale questions that we can answer. But we can do nothing without our wider community, and we work very closely with other researchers who are working in different disciplines to make sure that what we learn at the ecosystem scale makes sense for what is happening at the global scale. And this is also where we're coming up with new and improved techniques to do these global upscalings to understand how our planet is changing. And with that, I'll take any questions.
Is it on? Yes. Okay, great. Um, so I'm really interested in the dynamics of the degraded zones. And I don't know how much of this is established or that you could look at or that you haven't looked at or that is impossible to look at. But if you know anything about the amount of time you spend as a degraded zone, does that influence your likelihood of changing? If you're just a small isolated patch of degraded zone, but lots of other vegetated zones around you that can reestablish the population. Like, do you know anything about the dynamics of getting out of that degraded zone?
Yeah, your residence time.
Yeah.
Yeah. We haven't looked at specific numbers for residence times, but we do know it takes about a decade for the front line of the degraded zone to fully transition into a vegetated area that can become stable. But how quickly that happens will depend on what's around you, right? Because essentially what you're waiting for are are mangroves to move in, establish, and then infill in gaps. And so that takes a certain amount of time. And that residence time will be highly influenced by how much freshwater flows are coming in there. Because like I showed in Amanda's study, there are different rates of productivity. And if areas are not getting enough freshwater flows, it will take them longer to do the infilling process than other areas that are getting sufficient freshwater flows.
Yeah.
But it can take up to a decade.
But I wonder if you spend like 30 or 50 years as a degraded zone, if that's just so much harder to get out of.
It's possible for that to happen because there are certain parts of this landscape that remain consistent for even our time period, going back to the 80s, that were consistently degraded, and they remain degraded this whole time. And that will be largely influenced by whether the vegetation can ever infill. Because vegetation classes can go back and forth, even though you might see some improvement during some periods where flows are heavier, it could always go back during periods where flows are lower. And because that happens on about a 7-year cycle in this region, we see a lot of those transitions back and forth.
Following up on that, I was just going to ask if it's desirable or possible to use restoration, mangrove restoration, to speed up some of this transition, and whether that would be a logical strategy to take or feasible, or whether it just wouldn't make sense given the natural dynamics.
Yeah, I would say the biggest issue there is really the legacy, because people are really attached to landscapes looking the way they did in the past. And because of it, some of the management of the coastline is really based on actually keeping the salt water out, which you can't do. And what that does is it slows down mangroves from coming into areas. And when the mangroves do come in, because you also can't keep them out, a hurricane will bring in the propagules and they will establish and take over. But when that has happened in some areas, if that's not what they wanted that area to be, they will pull the mangroves out. And so because you have this constant fight with the legacy of what something should be and the future of where it's going, we're still in a place where we don't have a consistent strategy across the entire coastline. But it is possible that when these natural events happen, which they happen so frequently, I don't even think you would need to step in and plant more mangroves. Just with every tropical storm, they're coming in, they're moving forward, and that's just happening. If we just let it happen, the landscape would be in a pretty good place. And for most of the wetland systems where you see that they're failing along the coastlines, we have been able to track that has always been tied to a disruption in their hydrology. And it's our disruption of these natural processes that is reducing the resilience of coastlines. The coastlines could do this on their own if we would get out of the way.
Hi, thank you. I was wondering if the change of the water table can introduce sort of like trade-off in terms of soil carbon accumulation and also methane emission. Like say if you have high like wetter wetlands, you've got like higher carbon storage, but you also have higher methane emission. And if there is a trade-off, what's the sort of optimum level of water level? Thank you.
Yeah, so we have a project, myself and also with Pete Raymond, where we have been looking at fluxes of methane and CO2 at the same time. And what we've been able to show for a lot of ecosystems, even though you have to be concerned, wetlands are producing all of this methane, is it a problem? It's not, because when you offset it by how much carbon they're capturing as CO2, it's not that big of a deal. Even when you magnify the methane emissions by their warming potential, which is much higher for methane, but when you counteract how much carbon is being taken up by these systems, it will still be a fraction of that carbon capture that you wouldn't be able to use for something like credits. And so the ability of these systems to capture carbon as CO2 is much stronger than their warming potential as methane. And the real issue is that if you drain these systems and you let their legacy of carbon go into the atmosphere, that would be a huge problem. And once you kind of turn that faucet on, you're not turning it off. And so you would just have carbon being pumped into the atmosphere at a much higher rate than if the system was just producing methane.
Hey, Sparkle, really interesting surprise. I'm sitting here trying to figure out your climate debt work. And so I have a question. I have like a specific question as I try and figure this out. Can you explain what you mean by duration to me and how it's interacting with this optimal minus observed term?
Yes. And so the duration is how much time are you spending under these different water levels or submergence categories? And we added that term because without it, all you see is how much potential decline you have in primary productivity. But in reality, it's how much of a decline you see times how much time you spend in that condition. Because even if I have an extreme condition that only occurs for 2 days of the year, it might cause me some carbon loss, but it's not as big of a deal as if it occurred for half of the year. And so we added a duration term to the carbon debt calculation so that we can adjust for how much time are you spending under the different conditions. We're still waiting to see if this catches on. We just published this paper this year.
Marco, how much of the temperature sensitivity of methane uptake is just due to physical diffusion?
That's a good question.
And is that included in your model?
So the physical processes are included in the model. What's not included in the model is whether the rate of methane consumption will be high affinity or low affinity. And so most of the models that we built, we always focused on low affinity methane, meaning that methane concentrations that are being produced in that system are really high. And so you can live off of the amount of methane that's being produced, it's energetically feasible. But in dry terrestrial systems, methane can also be oxidized at really low atmospheric like concentrations, but we never put that into models because we thought it was constant and really small. Even though it happened over a large area, we really simplified it. But a lot of recent studies started to show from the microbial ecologists that it's very dynamic. And so you have to consider the temperature sensitivity in order to get it right. And our calculations suggest that that's actually true. When we put it in a process-based models, we do see an increase in performance, but we also see a pretty big enhancement in what the soil sink should be.
And that's mostly biological sensitivity.
Yes, it's biological sensitivity, not physical. We had the physical part down pretty well.
We are out of time because there's a class coming in. If anyone wants to continue the conversation with Dr. Malone, please join us in the dean's office between 2 and 3 for coffee and conversation. Thank you.
I don't know how to get out of this.